Now let's see how to solve a problem for a medium line. Let's consider a 230 kV three-phase transmission line, which has an impedance small z per kilometer equals to 0.05 plus J045 ohms. The length of the line is 80 kilometers, so we will consider it as a medium line. We will use the nominal pi model. Here, the shunt admittance is given by y small equals 3.4 times 10 to the power minus 6. Small because it is given in per kilometer. So we would like to calculate the ABCD constants of the two network model. We will calculate the voltage and current at the sending end, the voltage regulation, the voltage and the current at the receiving end, and the transmission line efficiency. When the receiving end load is 200 MVA at 0.8 lagging power factor, at VR equals 220 kV. So the total impedance of the transmission line is given by capital Z equals the small z times the length equals 4 plus J36 ohms. And the total admittance of the transmission line, just we multiply small y times the length of the transmission line. For the ABCD constants, we use the formulas given before. So for A, we find 0.9951 plus 0.000544J. The same we calculate for B, we calculate for C. The receiving end voltage per phase, we just divide by square root of 3 and we find the voltage VR per phase 127 with angle 0. For the complex power at the receiving end, we just write the three-phase receiving and apparent power into the complex form. It is 160 plus 120 MVA. So here the current per phase is given by the three-phase apparent power conjugate divided by 3 times the voltage per phase conjugate. And Vs is equal to AVR plus BIR is equal to 140.1 with angle 5.7 degree kV. The sending end line-to-line voltage, we just multiply the module of Vs by square root of 3 to obtain 242.67 kV. The sending current Is is given by CVR plus DIR, and it is equal to 502.38 with angle minus 33.69 degrees. The three-phase sending and apparent power into its complex form, it is equal to 3 Vs Is conjugate is equal to 163.179 megawatts plus 134 plus megavars. The voltage regulation, here we use the voltage at the receiving end at no load using the voltage divider law that we have explained in the previous part, and it is equal to 10.84%. The transmission line efficiency is found to be the power, three-phase power at the receiving end, 160, divided by the three-phase power at the sending end, 163, and it is equal to 98.052%. So this is an example about calculating the performance of a medium line.